So next up is the laws of logarithms. First, recall the following laws for exponents. So the product law states that if you have two powers of the same base, when you multiply, you keep the base and add the exponents. So we get ax plus y. The quotient law states that if you divide powers of the same base, you keep the base and subtract the exponents. And the power law states that you just multiply the exponents. So next we're going to look at what are the laws of logarithms. So let's start with the product law. A proof of the product law starts with let m equal the power a to the exponent of x and n equal the power of a to the exponent of y. So therefore log base a m times n is equal to log base a to the exponent of x times a to the exponent of y. Using our exponential rules, that's log base a to the exponent x plus y. So this is saying what exponent raised to a is equal to a to the exponent of x plus y. Well, this is the same as x plus y. That's our exponent. Second thing, well, what is x and y? Recall that m was equal to a to the exponent of x. Well, that is the same thing as x is equal to log base a of m, and n was equal to a to the exponent of y, which is the same thing as y is equal to log base a of n. So we get that log a m times n is equal to the log of base a to the m plus log base a to the n. So therefore, if you have log base a to the m plus log base a to the n, that's the same thing as taking the logarithm of a m times n. So this is the product law for logarithms. It's like the inverse of the product law for exponents. Multiply two powers of the same base, you add the exponents. Here, we add logarithms of the same base, we multiply the value within the logarithm. Alright, let's prove the quotient law. The quotient law follows a similar proof. We let m equal a to the exponent of x and n equal a to the exponent of y. So we end up with log base a to the exponent of x, a to the exponent of y. This gives me log base a of a to the x minus y. Similar to above, since we're taking the logarithm base a of a power with base a, then our answer is just the exponent x minus y. And again, same as the previous proof. We note that x is log base a to the m and y is log base a to the n. And therefore our quotient law for logarithms is that if we have logarithm of a to the m minus log base a to the n, that's equal to log base a to the m divided by n. So again, it's like an inverse of the quotient law for exponents. Instead of dividing and then subtracting the exponents, it's now subtracting the logarithms, and then we end up with division. And finally, the power law. So for this one, we're going to let m equal a to the exponent of x, and therefore m to the exponent of n is equal to a to the exponent of x to the exponent of n, and then using your exponent rules, this is the power rule, that's a to the exponent nx. So therefore, log base a of m to the exponent of n is equal to log base a of a to the exponent n times x. Again, we're taking the logarithm base a of a power with a base of a, so the answer is just the exponent n times x. And same as before, since m is equal to a to the x, then x is equal to log base a of m, and therefore we end up with n log base a to the m. So this is saying if that we have an exponent within a logarithm, we can bring it to the front of the logarithm. And this is our power rule. So therefore, if we have n log base a to the m, that's the same thing as evaluating log base a of mn. So notice for this one, if our exponent is actually sitting in front of the logarithm when we put it back into the logarithm. So let's go through a few examples to see why these are important. Note, with many of these calculations here, you would need a calculator to evaluate each. However, if we use the laws of logarithms, we can simplify these and then evaluate without a calculator. Our first example is log base 3, 6 plus log base 3, 4.5. To write as a single logarithm of base 3, we have log 3, 6 times 4.5, which is equal to log base 3 of 27. And again, to evaluate a logarithm, think of what exponent to 3 will give me 27, and therefore log base 3 to the 27 is just 3. 3 times 3 times 3. Next one, since we're subtracting, we can rewrite this as log base 2 of 48 divided by 3. That's log base 2 of 16, and log base 2 of 16 is equal to 4. 2 to the exponent 4 is 16. All right, next one. So this is log base 5 to the 25, and it is raised to the exponent of 1/3. So using our power rule, we can bring the 1/3 to the front of the logarithm. So this is 1/3 log base 5 to the 25. And this is 1/3 times 2, because log base 5 to the 25 is 2. So we end up with an answer of 2/3. D, this is log 10 times 10 to the 1/3. That's the same thing as log. Remember, this is an exponent of 1 on this 10. So powers of the same base, we add the exponents. So this is 10 to the exponent of 4/3. Using our power rule, this is 4/3 log of 10. And 10 to the exponent 1 is 10, so this is just equal to 4/3. Remember, if we don't see the logarithm, if we don't see the base for a logarithm, then our base is 10. And our final example. Now we can solve logarithmic equations like the one shown here. Our first step is always have one term on each side. So let's start with the left side. Using our product rule, remember that a logarithm plus a logarithm is equal to a logarithm of the same base, and we multiply the insides. So we have 5 times x. On the right side, we have log 81. We can bring that 2 into the second logarithm, so we have log of 3 squared. So now we have log of 5x equals, so now we need to divide. We have log of 81 divided by 9. And we have log of 5x is equal to the log of 9. And for this equation to be true, that means we only need to verify, we only need to determine when the insides are true, since they're both log base 10. So we're left with 5x is equal to 9, and therefore x is equal to 9 over 5. And there is the value of x. That makes the left side equal the right side. Remember, if you have any questions, please contact me, and here are some exercises from your textbook. Good luck.